In this lesson, we're going to talk about a very important rule known as the chain rule. The chain rule is probably one of the most important rules in all of calculus. On the surface, it allows you to differentiate composite functions like this one. A function in this form or this form is called a composite function. They occur whenever you substitute the output of one function into the input of another function. Now, formulas like this are great and everything, but I prefer pictures, so let me go ahead and draw this out for you. So let's try to figure out exactly what's going on here. This f of x we have here is exactly what you'd get when you take x and put it through f to get f of x. After this, we're taking the output f of x and putting it through g, just as we're doing here. The output of this whole process is this value over here that we call h of x. Now, when this was first explained to me, I just kept seeing these symbols f and g popping up everywhere, and I really had no idea what was going on. So, to make this a little bit more concrete for you, I'm going to use some actual examples to show you what's going on. Now remember, our goal is going to be to differentiate functions in this form over here, and to do that, we're going to need to find ratios change in h on change in x. So in this case, I've given you the function root 2x minus 1. I've decided to start at x equals 1, and we're going to use a change in x of 4. And we'd like to find the corresponding change in h. Now, to make this all a bit clearer, and to show you that it is really a function in this form, I'm going to go ahead and draw out a diagram of exactly what's going on. Okay, so the input to the function is x, and the output of the function is h of x. We don't usually look inside of functions, but it's going to be necessary for this example. So over here we have f, which gives us f of x, and then we sub f of x into g, which gives us h. So if you look carefully at this function over here, you'll notice that it is actually a composite function. The function on the inside is 2x minus 1, and then the function on the outside is root x. So for a bit of clarity here, we start off with some value of x, and then we put it through 2x minus 1 to get some random f of x value. After this, we can then take the square root of that value, and that will give us our value of h of x. To demonstrate this, let's use our first value of x over here, which is 1. Now we're going to put this value through this first function. So 2 times 1 is 2, minus 1 gives you 1 again. Now that we have this value of 1, we're going to now feed it through the square root of x. Because x is just 1, then the square root of 1 is also 1. Now, these values weren't particularly exciting, but they don't really need to be. They demonstrate the basic idea that you start with 1, put it through this to get 1, and then put it through this to get 1 more time. Now, we already said that we wanted change in x to equal 4, so the next value on the x-axis is actually going to be 5. Now again, we're going to take this number 5 and put it through the first function to get its position on the second number line. Now 5 times 2 is just 10, and if we subtract 1, we just get 9. And now that we have the second value over here, we can put it through the square root of x to get the last value, which is just going to be 3, because the square root of 9 is just 3. So we started with a change in x of 4, and we want to see what the gap is in f and in h as well. Now for f, we started at 1 and we ended at 9, so the gap is just equal to 8. And then for h, we started at 1 and ended at 3, so the change in h is just 2. And now we're ready to answer the original question. Change in h on change in x is just going to be 2 on 4, which is just a half. Now change in h on change in x doesn't seem to involve this middle value over here, but as we saw, we had to go through the middle value to get to the end one. To actually show you how the middle value is involved, I'm going to multiply by the middle value twice. So I'm going to multiply this thing over here by the number 1. But instead of writing 1 as the number 1, I'm going to write it as 8 on 8, because 8 on 8 is just 1. Now if we wanted to, we could just cross this 8 on 8 off, and we'd be back to where we started. But of course I wouldn't have done this if there wasn't a point to it. So what I'm going to do instead is I'm going to swap this 4 and this 8. Now if we look carefully, we're going to notice something that's really important for the chain rule. This 8 on 4 over here is just what you'd get if you divided change in f by change in x. And now, similarly, this 2 divided by 8 over here is just what you'd get if you divided this change in h by change in f. This actually tells us something reasonably important about this ratio change in h on change in x, which is just the ratio you'd get by going from here all the way to here. We're basically told that this is the exact same thing as the product of change in f on change in x, which is the ratio you'd get by going across this first function, and change in h on change in f, which is the ratio you'd get by going across this second function over here. So when you compose two functions like we did over here, all we have to do is multiply the ratios of each individual part. Now I can visualize the ratios here with little arrows across the functions. So again, just to clarify this, we're saying that change in h on change in x is the same thing as change in f on change in x times change in h on change in f. Now let me just remind you of something else. We said that this function over here is going to be called f, but this function over here, we wanted to call it g. Now this change in h here is what you'd get if you close the lid on the whole box, and you just look at the change from the input to the output. But it's also possible to say that the change from here to here is just the same thing as the change in g, because it's only gone through the function g. However, just to remind ourselves that we went through the function f first, we're going to label this as change in g with a subscript f. Now by replacing change in h for a change in g of f, I've really just changed the notation here, but it gets a very important point across. The idea is that to get this big change on the outside of the function, we multiply the two small changes on the inside of the function. And this function over here is g, so we might as well label this g. Now this actually completes our example, so let's go ahead and do this for the general case as well. Now instead of these letters over here, we actually had number lines on the example, so let me go ahead and draw number lines first. Now just like we had in the example, I'd like to start off with some point on the x-axis. Now, if we take this point x over here and feed it through f, we'll get a new point which we label as f of x. And now we take the point that came out of f and we feed it through g to get the point g of f of x as well. So now that we have the output value for the first point, we also need to find the output for the second point. To do this, we're going to start by moving up by changing x to get the next point. Now the height of this new point is just x plus this height changing x. Now to get the corresponding point on this graph, we have to feed it through the function f. Now because the old point we used was x plus change in x, then the new point that we have is just f applied to x plus change in x. So now we'd like to take this point f of x plus change in x and feed it through g to get g of f of x plus change in x. Now I'd like to label the change in position on the f-axis as change in f. And I also want to label the height over here as well. As we said in the example, if we look at the change when we go from x all the way to here, then we can label this change in h. But we can also say that this change over here is what we'd get if we took this change in f and then we put it through g. So we can also label this as change in g with a subscript f. Now in the example, we compared the changes as we went through the outside of the function and also as we went through the inside of the function. We said that the slope from here to here was called change in h on change in x. Then after this we looked inside the function, and then we saw that the change from here to here is just the change in f divided by the change in x again. And then finally we took this change in f and fed it through g to find that we got change in g of f. So the difference from here to here is just change in g of f divided by change in f. And then we came to the important conclusion. To get change in h on change in x, you can just multiply this number by this number over here. You can easily see this because the change in f's will just cross off, and change in g of f is the exact same thing as change in h, so you just end up with the exact same thing. And this is going to be an incredibly important step to actually help us take the derivative. So to find the derivative of h, we know that it's equal to the limit as change in x goes to 0 of change in h on change in x. But we also found that change in h on change in x is just the product of these two factors here. Now to continue this, we have to distribute this limit to both of these terms, which is something we can do because of the limit laws. And now if you look carefully at this, we've actually made some pretty good progress. This term over here is just the derivative of f with respect to x. So now we've dealt with the first term over here, but how do we deal with the second term? To do that, we're definitely going to need to make a side note, so let me bring out a little board to help us. Now if we want to simplify this, we're going to have to find an easier way to write change in g of f. If we just look at this value over here, we can see that change in g of f is the same thing as change in h, which is the same thing as g of f of x plus change in x minus g of f of x. Now after this, we want to pay attention to this f of x plus change in x. Looking at this value over here, we can see that f of x plus change in x is the same thing as f of x plus change in f. And therefore we can actually swap this for this, because it's actually equivalent. So now after this, we know what change in g of f is, and that's great and all, but we want a change in g of f divided by change in f. So let's divide everything by change in f. Now for those of you that have a really keen eye, you'll actually recognize this as something we've seen before. To help you recognize the formula, I'm going to get rid of the inputs to f. So if you look carefully, this looks just like the first principles formula without the limit in front. But we do actually have a limit over here. So when we actually take the limit of this thing, we're actually going to take it as change in f goes to 0. Of course, if change in x is going to 0, then change in f also has to go to 0 as well. And that means after taking all the limits, this thing over here is going to end up being the derivative of g with respect to f. And so this formula that we've just highlighted over here is the final form of the chain rule. So we can go ahead and get rid of the side note for now. Now I don't really know if I can give formulas awards, but I'm going to go ahead and label this one of the most intimidating formulas I've ever seen. But if you just put your intimidation on hold for just a minute, I'm going to show you that it's actually a really easy formula to use, and I'll do this with an example. So in this example over here, we'd like to differentiate this function, 3 of x squared plus 4 all to the power of 3. To do this, we first have to recognize that this inner part can be called f of x, and the outer part would be g of x. So to make our lives easier, I'm going to go ahead and write out the formula first. So dealing with this first term over here is actually really easy. We just have to find df on dx, and f is just this part inside. So now that we know f of x, we can just differentiate it directly to get df of x on dx. This 3x squared will just become 6x, and this 4 will go away because it's a constant. So now we've found the first half of the derivative, and that was pretty straightforward. But this second half is really the intimidating part, and that's what we really want to figure out how to do. Now to make it easier to actually find the derivative, I'm going to relabel this part with a script f. Then by that logic, instead of writing f of x everywhere, we can write this script f instead. So now we just know that g of this scripty f is just f to the power of 3. And finding this derivative is also going to be way easier, because we can replace this f of x for this script f. So now we just need a bit of a careful eye. We notice that g of scripty f is just scripty f to the power of 3. And what we're after is the derivative of g of scripty f. So all we have to do is differentiate this term over here. And finally, we just remind ourselves that this scripty f is the same thing as 3x squared plus 4, so we can replace that as well. And now we're ready to write down the derivative. We know that it's just this term, which is 6x, times this term, which is this term over here. So we just get this. And therefore, the derivative of this expression over here is just equal to this expression over here. And now, if you're anything like me, you probably looked at all of this and thought, well, that was way too much work. So I spent a lot of time looking at these problems and trying to find shortcuts, and eventually I came up with one that actually led me to a much deeper insight of exactly what's going on. Now, I hate to do this to you, but this lesson is getting a little bit long. So if you'd like to learn the easier way to differentiate functions like this one over here, then you'll have to join me for the next part, where I'll show you how.